All right, this is going to be a quiz recap of the 42920 free body diagrams quiz, and I'm going to get right through it here. So you're going to see my view of when I actually make the quiz. Okay, that's how I'm going to go through it today. So we have some instructions. It says it covers material from Unit 2.1 and Activity 2.1.3. That is the activity that I did on Wednesday in the help session. The quiz is timed and open notes. Please retain your scrap paper and put your name at the top and the assessment date. And then it says to prepare, you should review free body diagram practice handouts, video lectures, and concepts we've discussed. Make sure you can successfully hit the following two learning objectives, right? I can draw accurate free body diagrams, labeling the forces involved. So that was a lot like what we did on Wednesday with practice problems. And I can interpret free body diagrams to show forces acting on an object, calculate the net force on the object, and predict the object's motion. So that was also a lot like what we did on Wednesday in the help session. Okay, so I'm going to point out now that you would have only gotten three, so you got all three of these questions here, but you probably got them in different orders. And then down here, you would have gotten just one question for 2 points. And then down here, it says pick three questions, 2 points each. 1, 2, 3. Okay, so you got all three of those. And then here at the very bottom, it says pick two of these questions. So you may not have gotten all, you definitely did not get all four of these. So that's why I'm going to go through them though, so that you can see that. Okay. Okay, so this says when creating a free body diagram, a built-in end cantilever support. So these are vocabulary. This group here is all vocabulary, but it was also covered in Wednesday's practice problems on slide number 2, actually, of what we did on Wednesday. So when creating a free body diagram, a built-in end cantilever support is represented, and then it says select all that apply, all that apply. So your options were a vertical force, a horizontal force, a moment force, or none of these. And the correct answer would have been a vertical force and a horizontal force and a moment force. And I would direct you back to my lecture from Monday and Wednesday's videos where I covered it. And it's also in the PowerPoint as well that you have. Okay. The second question, also vocabulary S, okay, says when creating a free body diagram, a pin support is represented in the free body diagram with, and it says select all that apply, and we covered this, and a pin support is supported in the vertical, in the up and down direction, and the horizontal direction. It does not these two. Okay, again, these are just vocabulary, so there's not a lot for me to really break down in these. It was just went over it, didn't practice problems. You had to just review your notes. And hopefully you had it in your notes because it was an open note quiz. So a tension force replaces what objects when creating a free body diagram? And also that was covered in Wednesday's class, also in your PowerPoint, also in the Monday lecture. A tension force replaces a rope, a chain, or a cable. We would replace those with a tension force. Okay, group 2. So this says, choose the correct free body diagram for the image below, and you were given several to choose from. Okay, so you were given this guy, that's the main picture, and then you were given a couple of options. So you were given this as an option, this is an option, this is an option, and this is an option. Okay, and this one is the correct one. And Kate had even asked in class, but basically it doesn't really matter what direction I draw this arrow in. Technically, I should assume that it's a positive force, and I really should have drawn it in the right, towards the right, but it really doesn't matter. What I'm saying is that the roller joint is replaced with a perpendicular force, right? Roller joint is replaced with a perpendicular force, and the pin joint is replaced with a force in the y direction and in the x direction. and then I had to label the force that was in the original picture with the amount and the arrow also. Okay, so that was the correct answer there. This represents 2 pins, right? A vertical and a horizontal, a vertical, and that's not what's in the picture. This one represents 2 rollers, so just 2 perpendicular forces, and it's not what's in the picture. And this represents probably what you got wrong, if you got this wrong, was that you got the roller and pin backwards, which again should have just been in your notes from Monday and Wednesday's lecture. But the roller and the pin, if you recall, so the roller has a single perpendicular force, does not have this, and the pin joint has a vertical and a horizontal. So this would have been the correct answer. Okay. Okay, next it says, in the which one of the following free body diagrams depicts an object accelerating to the right? Choose all that apply. And the correct answer here would have been B and D. Okay, this is not accelerating to the right. It's actually sitting still because something's pulling up on it and pulling down on it equally. This is sitting still because it's being pulled up and down at the same amount in opposite directions, and to the right and to the left in opposite directions. So it would stay still. This one would go to the right because it's being pulled harder to the right than to the left. Bigger arrow tells you that. And this one would move to the right because there is no force pulling it to the left. So B and D. Okay. In the diagram below, which free body diagram represents an object which would be at rest, meaning not moving, right? And the answer here would be A and C. So as I said in the previous one, A, these are all cancel each other out, and C, they cancel each other out. So the box does not actually move, or the object. Okay. Sliding book. So which of the following cases does the free body diagram below best illustrate? Okay, so best illustrate. What does this best illustrate? And we have a book sliding across a table at a constant speed, a book sliding across a table at a slow and slowing to a stop, or a book that has fallen from a table. So let's talk about that. It's not slowing to a stop because it's not like there's a force pulling it to the right, right? Applied force means that you're applying force. So you're pulling it to the right or pushing it hard to the right, and then friction is slowing it down. So friction would have to be bigger than the applied force if it were slowing down, right? Think of something very heavy. You go to push it across the desk, you apply force, but then friction slows it down. And I lied. Yeah, that's correct. And then this one is correct. It says it's a book sliding across the table at a constant speed. So here I pull in one direction to the right at a constant speed. So like 5 pounds of force to the right, and then there's friction of 5 pounds of force that's pulling in the opposite direction, right? So I have an applied force in this direction and friction. This is very similar, by the way, to a book. So you could have thought, well, this thing's not moving because the applied force and the friction force are equal. And really what you'd be saying is that it has a constant velocity of 0, right? So it has a constant velocity just of 0. So this is moving across the table at a constant speed, okay? It might be 10 miles per hour. It might be going 10 miles an hour this way, with 10 miles an hour of friction that way, but it is moving at a constant velocity, okay? So it's really the only one of the 3 that made sense there. A reminder that all free body diagrams are diagramming blah, 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 blah. So here it wants to know what is the net force. So what's the total force acting on this box? And you should have said 6 newtons south, because this and this cancel out. This is down and this is down, so 6 newtons south. Right? That should have been your answer, 6 newtons south. Okay. A reminder, so similarly here, what they want to know here, and this one should be 0 newtons because cancels out, cancels out. So 0 newtons. It's in static equilibrium. A reminder that, okay, so what is the net force here? And you should have gotten 70 newtons west, 70 newtons west as your answer, because this is pushing 70 newtons harder to the west than this is pushing to the east. And the last one, you should have gotten 170 newtons to the east, 170 newtons to the east, because they're both pushing to the east, right? So both pushing to the east, 50 newtons, 120 newtons, 170 newtons to the east. Okay, that's it for today. And I hope that all made sense to you. And if not, feel free to shoot me an email and I can try to further explain. Okay, thank you.